So most of my time at SoundCloud, I'm actually not putting sounds into the cloud. Contrary to common belief, I work on monitoring most of my time. And in my happier moments, I work on an open source monitoring system called Prometheus. We started that, or somebody else started that, later in the acknowledgement, in 2012. It was open source from the beginning, but we only made noise about it in January this year. And then we quickly grew a quite awesome community, very qualified, very committed, almost like the Go community. There's obviously a big overlap between those two communities because it's implemented in Go. I mean, we can test it. Who here in the audience has a vague understanding what Prometheus is? Hands up. 10%. Not too bad at all. For everybody else, I unfortunately can't explain how to do monitoring with Prometheus because this is, after all, the Go conference and not a monitoring conference. But despair not. Where are my slides? Oh, there. We have a pretty decent website which has all the explanations. There actually had been introductory talks about Prometheus as a monitoring system. They have been recorded. They are linked from the website by many different people. So just go there and you will see all the goodness. For now, we'll focus on Go. So the idea here is we pick a few of those boxes from the architecture diagram, boxes that are implemented in Go, and then I'll tell you about lessons learned, design decisions, why did we choose Go for that component in particular, and why we never ever, or at least almost never ever, regretted our decision. The natural entry point will be the client library. That is where you instrument your code with that library to create metrics which you present to Prometheus. It's a bit like GoKit. You could use GoKit, as we have seen in Peter's talk, but that's kind of one level further down. A client library has to be in the language of the code you want to instrument. So we have many different client libraries. Of course, we will focus on the Go client library. It's easy to write other client libraries. Part of the reason is that in Prometheus, you monitor, or your metrics on the client are really low level. You count things, for example. And then all the processing and aggregation and everything is done on the server side. So let's talk about counters. Counters are a very fundamental metric type. They only ever go up and they count things. So in Go, an interface would look like that. And that's actually not would, the interface looks actually like that. I elided doc comments and a few details, but that's basically the code. So the counter is an interface that has an embedded type metric. I will talk about that in like 12 seconds or something. It has an increment method that increments the counter, and it has an add method that increments it by some value. Because it only ever goes up, it will panic if you try to decrement it. That's all written in the doc comment, which are not quoted here. So metric, embedded type. At the bottom, you see metric is another interface. It has a write method with a very strange DTO. That's a data transfer object. So that's Prometheus specific. Prometheus belongs to the church of pull-based monitoring systems. So the server decides when it wants metrics from you, and then it comes along and scrapes you via HTTP. In that moment, you have to do something as a client. And the client calls this write method, and then the counter will put its value into that data transfer object. So pretty specific to the way Prometheus works. Implementing that, very straightforward. This is a naive implementation. You put an integer into a struct that counts things. Then the add method is easy, right? If our increment v is negative, we panic, as promised. If not, we increment our value. I'll spare you the details about the write method because that would go totally into details of the data transfer format of Prometheus, but there's no magic in it. So let's actually not spoil the surprise. This looks quite good, very easy, but it has a problem because it's not Go routine safe. You might ask the user to only ever call add from one Go routine, never concurrently, then we are fine. Actually, we are not, because the Prometheus server might come along and scrape us, and then we need to call the write method, and that will probably happen in a different Go routine. So we kind of want to be Go routine safe, and the most straightforward way to do that is mutexes. That's totally not Go-like, right? But in the sync package, we still have mutexes. It's very low level, but it does its job. It's very easy here. So we add the mutex to our struct. Whenever we enter a method, we lock the mutex, then we defer the unlock. You've probably seen codes of that kind a million times. And that's basically it. That's the only modification we need. Little note, in the write method, the counter, it has a pointer receiver now. I leave that as an exercise to the reader, why we need that. So this looks good, right? So we are kind of done implementing a counter, and we can now pick another box from the architecture diagram and talk about something more interesting, except performance. So performance matters in general, of course, but if you write a client library and that client library is used in hundreds, if not thousands of programs by others, you really want to screw up performance. Also monitoring, right? You don't want to force your users to spend most of the time in monitoring. It should basically not be noticeable at all. So to optimize performance, we have to write benchmarks, and benchmarks in Go are easy. This is completely by the book, what you can see here. You see the command to run at the bottom. You see the code here. The only specific thing that you should notice is that we are not only benchmarking the add method, we are also calling the write method now and then, every 1,000th time, actually, because that's how Prometheus works. In Prometheus, the client counts and counts and counts, and now and then, like every minute, the Prometheus server comes along and scrapes your metrics. So then the write method is called. So easy, right? So let's run that. The naive counter that is not Go routine safe is super fast, 5 nanoseconds. I actually wanted to put the Grace Hopper picture here. Glad I did not, because it was in the other talk. So that's pretty fast, right? And it's probably mostly overhead function call. Even the for loop in the benchmark might matter. Our mutex counter is frustratingly slow compared to that. On the other hand, 150 nanoseconds, that might be OK, right? Perhaps we're fine. The problem is our benchmark is not very realistic. Why did we introduce mutexes in the first place? We introduced them to be concurrency safe. Our benchmark is not concurrent at all. We need a concurrent benchmark to actually see how fast this is. So the code gets way more complicated. I'm not going through every single detail. Just note that our helper benchmark function, benchmark add and write at the top, has now a concurrency argument. So we start Go routines in that function. The number is the number we pass in as concurrency. And we have a tricky use of wait groups to not let those Go routines start right ahead, but we wait for all the Go routines to wait. And then we call this start.done at the bottom, and then we unleash the stampede, and our poor counter will be incremented by I don't know how many Go routines. That's what we do in the actual benchmark function at the bottom. The command at the very bottom has a new flag, -CPU. That turns concurrency into parallelism because it tells the Go tool to run on multiple CPU cores. It sets basically Go max procs to those values, which sometimes is actually important. It's also a good time to try out the race detector to see if all your races are gone. Don't do that when you want to benchmark, like get real timing because it slows down things, but do it to find out if your races are gone. So, results. That looks interesting. So the normal case, 1 Go routine, 1 CPU core, same as before. And even if we set up Go max procs to higher values, nothing changes. That's good. Unfortunately, if we start many Go routines, things degrade a bit. On only 1 core, that's fine. It's probably just scheduling overhead. The Go runtime is doing the right thing. But if you run this inherently sequential process on multiple cores with multiple Go routines, you get lock contention, and things get really bad. They might get a bit better in Go 1.5, but the lesson here is if you do something that's inherently sequential, highly concurrently, and in parallel on multiple cores, you can only lose. OK, so again, 1,100 nanoseconds, that's 1.1 microseconds. We've just seen in one of the previous talks, that's still not much, right? Does it matter? Is that a problem? Let's check. So what is this? This is the Prometheus expression browser. If you can read the fine print, and if you know Prometheus, you can already guess what's displayed here. This is Prometheus monitoring itself, and it calculates the rate of samples ingested per second. So this Prometheus ingests 360,000 samples per second, which is nice. And there's a lot of engineering effort behind that, but I won't talk about that right now. We just talk about how to monitor that. We monitor that by incrementing a counter. Whenever we ingest a sample, we increment that counter. So now let's do the math. 360,000 samples per second, 360,000 counter increments per second, probably from many Go routines, because we only can reach that nice result with a lot of Go routines and a lot of CPU cores. So they all try to increment the same counter. Every increment probably takes like a microsecond or 1.1 microseconds. We do the math. We end up at 400 microseconds. We need to increment the counter out of every second. Too bad, right? So, I mean, our monitoring system, monitoring is like measurement in quantum physics. Whatever you measure, you will influence the target, but it should not steal half of your time, right? So we are stuck. Something is wrong here. Whenever you're in a situation of desperation, you should fall back to the Holy Scriptures. Do not communicate by sharing memory, share memory by communicating. That was quoted before at this conference, obviously, right? So perhaps we did it all wrong. What did we do? We had many Go routines, 1,000 Go routines that were all trying to increment the same counter, the same piece of memory. So what we should do, we should have one Go routine that manages that piece of memory, and then all the other Go routines should send messages via channels to that one Go routine. Please increment the counter, or please give me the value of the counter. Let's do that. So this looks like real Go code, right? So now we have a struct that has an in channel, which may or may not be buffered. I'll talk about that later. That has an out channel, which must not be buffered. And then our add is very simple. We send the increment to the in channel. The write method will read from the out channel the current value of the counter and does its magic. And then we have an additional method, which is private. It is run as a Go routine. It's called loop because it loops forever. It just runs that select statement, and whenever somebody writes something to the in channel, it will take it and will increment the value. And when somebody wants to read from the out channel, it will send that value to the out channel. Easy, right? Looks like real Go code. But will it blend? So let's run our benchmark. The answer is meh. I mean, it works, but all those numbers have gone up. I mean, it's kind of academic interest how the first number, by the way, is the synchronous in-channel. The second number is the buffered in-channel. How in different situations those different in-channels perform in a different way. It's also interesting that the hard case, where we have a lot of CPU cores and a lot of Go routines, the difference becomes, to the mutex counter becomes smaller. The simple case, the difference is actually pretty big. So, I mean, we refer to the Holy Scriptures, and now we are still in trouble. So what happened? We applied a high-level, very powerful concept, or I've learned it's an intermediate-level powerful concept, channels, which is great to build up communication architectures. We applied it to a fundamentally really low-level problem, increment an integer, which is like, it's kind of the most low-level trivial thing you can imagine, right? If we only could atomically do that and not like unleash all the power of channels. I mean, channels are not just fast mutexes. They are kind of slow mutexes, if you want. They are done for something else. So, wishful thinking, we want to atomically increment the integer. If we dig down into the sync package, there's sync atomic. And that gives us CPU instructions at our fingertips where we can actually do that, exactly that. We can atomically increment an integer. We can atomically read an integer. If we use that, our new counter implementation looks almost like the naive counter from the beginning, except it's Go routine safe. It's all atomic. Dream, right? Let's benchmark it. And that looks really good, right? So all of a sudden, we are almost as fast as like no locking at all. We are doing the right thing, apparently. I mean, it's still like lock contention is still a factor of 3, but we are 25 times faster than the mutex counter, not to speak about the channel counter. So but it looks pretty good. And it kind of, it's interesting that you have all those intermediate level concept in Go, but you can still do a really low level thing. And I can use CPU instructions that atomically increment integers. So I guess we're done, right? We can pick another box from the architecture diagram and talk about something interesting. Except I lied. So Prometheus, for some reason, uses floats as sample values. So you might think, why do we use floats for counters? I mean, Sesame Street, the count, he counts 1, 2, 3, 4, 5, ha, ha, ha. So it's why would we count with floats? The reason is we do. Let's imagine you want to count the seconds you have spent serving requests on your server. So I served the request in 250 milliseconds. I'm glad. I increment my counter by 0.25. That's a float. Now we could just have a fast integer counter and a slower float counter or something, but in Prometheus we decided we want to do everything with float because it basically works for everything, so we are good. Unfortunately, there is no general purpose function to atomically increment a float. So what do? We're again in trouble, right? We have to play tricks. I call that the compare and swap gambit. So here we are. It's a three-part trick. First part is we will not save the float in our struct. We will save a uint64, which is the bit pattern of a float. It takes the same amount of storage. It's actually on the bit level. It's the same thing. But for Go, it's a uint64. And then please look at the bottom. I need a laser pointer, but I don't have one. And I have two screens to point to. So the bottom, the right method, that's the easy part, step 2 of the trick. So we can atomically read the value bits with atomic load uint64. And then there is, in the math package, a handy function to convert a bit pattern into an actual float. So we do that, then we have the value, we do the magic that we need for Prometheus, and done. The other problem is, how do we increment the float atomically? And that's the add method. And that's a bit more complicated. Stay with me. So first of all, you read the old bit pattern. So you load uint64, the value bits, fine. Then you calculate the new bit pattern by converting that bit pattern into a float, add our increment, and then convert it back into a bit pattern. So you have the old pattern, you have the new pattern, and now you could just write the new patterns into the variable, but that would not be coroutine safe. So now the trick, right? The atomic compare and swap uint64 function, very fancy name. What does it do? It reads the old value bits in the variable, compares them to the old bits. If they're the same, it will swap out the new bits with the value bits and return true, and we are done. And that's all one atomic operation. If another Go routine has incremented the counter in the meantime, the old bits will not be the same as value bits anymore. It will return false, and we just try again. Done, right? I mean, it could go horribly wrong and spin a lot. So this is why we have benchmarks. So let's benchmark that. Not as good, not as glorious of a victory, but good enough, right? I mean, I guess it's fine, right? It's still an order of magnitude better than the mutex counter, and that's good enough to count 360,000 samples ingested per second. So let's declare victory. Let's pick another box. And it never ends. One last thing, the Holy Scriptures have fine print in the tech world. It's usually at the bottom and called known bugs or something. We kind of read that even, but we skimmed over it, and it was talking about 32-bit architecture, and who's doing that nowadays, whatever, right? We kind of forgot about it. And then we accidentally compiled 32-bit binaries for Linux, and it crashed in the weirdest possible ways. So what's the reason here? On 32-bit architectures, you have to 64-bit align your 64-bit integers, and you can do that by putting it first into a struct. So it's easy, but you have to think about it. Then this is a client library, so people might run this on weird platforms. So it actually matters. And after we have learned our lesson, we checked out code on GitHub, and in fact, many people are doing that wrong. So if you use the atomic package, check your alignment tomorrow or today or whatever. People will run your code, and they will run it on Raspberry Pis. And in the case of Prometheus, a crazy guy, he's called Fish. He's now Docker. He's one of our early contributors, inner circle of pre-announcement contributors. He runs Prometheus, the whole Prometheus server, not just a client, on a Raspberry Pi. And I think it's also a great thing about Go, right? You can run you have a modern language, and you can run modern, very complex software on a low-level platform like a Raspberry Pi. Great stuff, but you need your alignment properly. Okay, finally, we can pick another box in this thing and we can talk about something actually interesting, but I guess we are almost out of time. So despair not, again, this conference has a hack day, so there are many Prometheus developers and Prometheus users, as we've seen here, so we will huddle in a corner on Friday, and we can talk about all the advanced stuff and Q&A and whatnot. Also, since we have so many Prometheus developers here, we want to socialize a bit, so we will meet tomorrow at 7 p.m. at the Great Bear, and we will find ourselves a place to socialize. So if you want to join us and discuss Prometheus over a beer, tomorrow 7 p.m. at the Blue Bear, or just do it during Hack Day. So this would be the honest title of this talk, how to increment a numerical value, or how simple things can be damn hard. I still want to use the last few minutes of this talk to not go through all the other stories that are in those yellow boxes from the architecture diagram, but just give you our lessons we've learned about performance optimization. So number one, not particular order, but pretty important, allocation churn. So once you have run your benchmarks, and they do concurrency and they do parallelism and everything, you can also benchmark heap allocations by adding dash benchmem. Really easy. Most of you know that probably, but allocation churn is a bad thing. You might have multiple seconds garbage collection pause time. I mean, that will all be solved with 1.5, I guess, but still, if you have a heap allocation that could be avoided by just writing your code in a nice way, you should do that. So run those benchmarks. At some point, you will find code that you think should never allocate anything on the heap, but it still does. And that's because the compiler does escape analysis and is smarter than you in doing that, so your local variable is actually not that local. If you run into that problem, you are not smart enough, you can ask the compiler. That's dash gc flags equals dash m, right? So then the compiler tells you about its escape analysis, and you realize how smart the compiler is and how dumb you are, and you will fix your code, and your allocations are gone. So second lesson, pprof. You probably all know pprof, but I guess many of you do not appreciate as much as we do. This is just pure awesomeness, right? You add this one line to your code, and if you have an HTTP server running, you can use those endpoints to do runtime and allocation profiling. It's almost no cost. You can just switch it on all your production binaries. If they misbehave, you can profile them. You also have like Go routines, stack dumps, and everything. It's just great, has helped us so much to solve bugs and optimize Prometheus into that thing it is today. It gives you those nice call guides. That's from the real Prometheus, beautiful in a way. And the third thing is a bit more obscure. It's very tempting at some point to use C libraries in Go because frustratingly, sometimes they are faster than the Go implementations because they are more mature or they use fancy C stuff. CGO is a very easy way to call C libraries. We did this in Prometheus for LevelDB, which has an awesome C++ implementation. You lose certain advantages of the Go build environment, so you are back in makefile, shared libraries, long compile time, whatever. But anyway, that's kind of organizational. But it also has a per call overhead. For a C Go call, you have to switch from the Go universe into the C universe and back, and you have to shovel data back and forth. So ideally, you have super expensive C calls that shovel a little bit of data. But Prometheus was kind of the opposite. We had super fast LevelDB calls, and we shoveled a lot of data. We learned it the hard way, and only 2 months after that, somebody wrote a nice blog post about exactly the same story. I mean, not LevelDB, but the general thing. It's still a good read. It was just too late for us. Okay, this is why I'm sharing this with you now. Finally, let's wrap things up. Special thanks to Matt Proud and Julius Foltz. They are both in the audience. They are the founding fathers of the project. They started that completely crazy as a pet project in their living room, even before SoundCloud adopted it as their standard monitoring system. That was the word. So great shout out to them. Without them, nothing of that would have happened. Now we have like 1 minute and 30 seconds for questions. And ask me anything. If the questions are too hard, I will just ask Julius because he knows them all. Thank you.